Well, one thing we haven't used so far in writing our Lewis structures is the rule that talks about how the least electronegative atom is the central one. We haven't had to worry about it yet. Well, let's go ahead and set it up now. First, here's the definition of electronegativity. It's that attraction potential between the two atoms that are bonded to each other. And it talks about the distribution of those bonding electrons. The two hydrogens share that bonding pair of electrons equally. And so in the mathematical description of that bond, the electrons are spread out equally on average. And that's what I'm attempting to show here by that shadowed outline. Now you take hydrogen fluoride. And fluorine has a very high electronegativity compared to hydrogen, which means that it strongly attracts those bonding electrons. So now because of that attraction, it doesn't turn it into the fluoride and the hydrogen ions, but it does mean that there's an unequal sharing of those electrons. And that's what I'm trying to show by the shading now. Notice how it's shaded much more darkly around the fluorine than the hydrogen. And if you were to take partial charges and put them on here, then you'd say the fluorine end is a little bit negative and the hydrogen end is a little bit positive. And that's going to have much more of an effect on what we do later on when we specifically talk about dipoles and polarity and hydrogen bonds and things like that. We're just kind of setting this up so we can use electronegativity in a bit to try and explain observations. Let's take the molecule CHCl3. And if I tell you that there's one central atom and the rest are surrounding it, just right off the top of your head, there appears to be three different choices. The one on the left, I have carbon as a central atom. The one in the middle, I have hydrogen as a central atom. And the one on the right, I have chlorine as the central atom. You can eliminate one of these choices immediately. Which one is it? Well, it's the center one. Hydrogen can only make one bond. We set that up earlier. So now we have these two choices. Carbon is the central atom or chlorine is the central atom. Well, in order to get an idea of what atoms are involved in the compound and then how they're connected, we have two big tools. The first tool is the mass spectrometer. And this will tell us what atoms are actually in the molecule first. So if you notice this setup, you make your sample there on the left into a gas, and then you ionize it. You knock off one or more electrons. And then you have this ion beam. And once you've accelerated those ions, and we're going from left to right, you then deflect it using the magnet. Now the particles that are heavier will experience less deflection than the particles that are lighter. So if you look in the upper right of that diagram, you get multiple beams coming out of this because of the different masses. Now this is using magnesium as an example, but it can be for anything that you can turn into a gas and ionize. So we can get an idea of the different particles based on our knowledge of isotopes and where the beams hit. Here's a sample mass spectrum of CHCl3, trichloromethane. And we've got at least 4 main areas on here. Let's look at what these different areas are. I'm not going into an in-depth description on how to read a mass spectrum, but this is just a brief overview. So we look all the way to the right. This is our molecular ion peak, and it's centered around 118 for the mass. And so that's the whole molecule just with one electron knocked off. So that'll give you an idea of the mass of your species. Now the reason why we have various ones on there is because chlorine has two main isotopes, chlorine 35 and chlorine 37. This next peak, what has happened is for some of them, when you made the ion, a chlorine got knocked off. So this is a fragment peak. And it's centered around 83. And if you add up the masses, you'll see what I mean on that for this CHCl2. Then we have another fragment peak, which is the loss of two chlorines. And it's centered around 48. And then finally, we have another significant peak, and this is the halogen peak for chlorine, for a +1 charge. Now if you're looking at it saying, well, wait a minute, chlorine makes a -1 charge when it makes an ion. No. We're inducing charges by knocking electrons off. And you can see here, we've got the two main peaks, 35 and 37, and that corresponds to chlorine 35 and chlorine 37. The chlorine 35 isotope has a percent abundance a little under 76%, while the chlorine 37 isotope has a percent abundance a little bit above 24%. So with enough experience, this would tell you that you have carbon, hydrogen, and 3 chlorines bonded together. And that's what each of these main areas is representing. Now it doesn't tell you how they're bonded up though, it just tells you that you have them. So now in order to tell how they're bonded, you can look at an infrared spectrum. And what happens on this is you apply infrared energy to a gas phase molecule and you scan the spectrum, and these areas correspond to absorption areas, and you get molecules that will vibrate. And how they vibrate depends upon how they respond to the infrared energy. So you look all the way on the right, that broad peak there, that corresponds to a carbon-chlorine stretch. Then, this one over here to the left, that corresponds to a carbon-hydrogen stretch. Now look at the information that we get out of this. We know that there's a carbon-chlorine stretching motion going on, and we know that there's a carbon-hydrogen stretching motion going on. That's important. Let's look at these two stretches. Here's the CH stretch. The white on the top is the hydrogen, and the gray one in the center is the carbon. And let's look at a carbon-chlorine stretch. The green ones around the outside, those are the chlorines. So now we only have one choice for how the atoms are hooked up, because carbon has to be bonded both to hydrogen and to chlorine, and the only way to do that is the attachment scheme on the left. Make carbon the central atom. Well, we can use something to help us with this, and it doesn't work all the time, but it's a decent predictor. Here's a table of electronegativities. Now this is using the Pauling scale. There are a number of different scales. You don't always have to have the numbers. If you're trying to find out which atom has the higher electronegativity or which one has the lowest value for electronegativity, a lot of times you can just look at trends. So let me show you a few graphs here briefly so you can see trends. Okay, so these are electronegativity values on the left plotted against atomic number on the bottom. And it looks like a bunch of chaotic dots. But there's information here. Here we've got rows or periods. And you can see some trends going on here. Look, as you go from top to bottom, that's the same as going right to left in a period. And you notice trends that the electronegativity is decreasing. And okay, it doesn't work all the time. I mean, if you look at bromine to potassium and iodine to rubidium, you see that weird jumpy area in the middle. That's due to the d electrons. And there is actually some extra information in there, but we're just not going to talk about it. Okay, and then if you look at acetine to cesium and nobelium to francium, you also have an additional problem because you've got F electrons involved there. But it's still not a bad pattern. High value of electronegativity on the right, relatively lower as you go from right to left. Then if we look at columns, you can see there's a rough trend. Top of the column, fluorine, more electronegative. Bottom of the column, astatine, lower value for the electronegativity. So it's not bad. Not bad. Okay, it doesn't work all the time. There's column 4A, carbon all the way down to lead. That rightmost bolded one is lead. Oops. Okay, it just means you can't use this all the time, and you can't, as far as trends, it's a rough trend. It's much more complicated than just saying greater at the top and greater at the right. But it works a lot of times. So based on what we see there, we can then give an approximation and saying, if you have a choice, and first remember, hydrogen is not your central atom, but if you have a choice, typically the least electronegative goes in the center. If something has a lower value for electronegativity, that means it has a greater ability to share electrons than those with a high value of electronegativity. So you would want a greater sharing potential in the center than on the outside. And this doesn't work all the time. NBr3. Nitrogen is the central atom, and you get the 3 bromines around nitrogen. But if you look at the electronegativity values, nitrogen has a greater electronegativity than bromine does. Okay, so it's not perfect.